Hello everyone, my name is Dr. Omar Shehab. I am a researcher at the Theory and Algorithm team of IBM Quantum, which is located at IBM Thomas J. Watson Research Center at New York. Um, Today I will be talking about uh, basic ideas which kind of is used to develop the concept of near-term quantum computation. I will also give you some exposure to how to program near-term quantum computers and a little bit about future of the field. Um, the title is a little bit loaded. Here, friendly means it is friendly to the people who comes from mostly computer science and electrical engineering background, uh, um, um, rather than from physics background. Typically, when people talk about quantum computing, there are lots of physics terms. There are lots of assumptions about knowledge in of the foundation of physics. So I will try to focus more on computer science part of the field. Um, and although I kept quantum computing in the title, it will be focused mostly on near-term quantum computing, which is kind of the next natural topic to discuss now that you already know about Simon's and Shor's algorithm, which needs fault-tolerant quantum computing to implement. So here's the structure of today's lecture. First, I will kind of brush up the basic concepts of quantum computing. Then I will give you some idea about what the device actually looks like, the scale and what are the components, then what are the target problems we're focusing on in near-term quantum computing. Then I will also talk about the basic ideas of near-term quantum computing, how it is different from traditional quantum computing. Then I will give you one example, how we solve problems using near-term quantum computer. Finally, I will talk about the future of the field. All right, so what is quantum computing? So as you all probably already know, it was originally proposed by Professor Richard Feynman in early to mid 80s through a couple of papers. So there are two papers. One is quantum mechanical computers, and another one is solving problems with physics. So in these two papers, he basically argued that since simulation of quantum mechanics is very hard on a traditional classical computer, why don't we build computers which follows the based on the principles of quantum mechanics? So that way, you're basically simulating a quantum system using another controlled quantum system. So that was his original idea. So that he made that argument in the first paper. Then in the second paper in quantum mechanical computer, he actually showed a mathematical model to do that. So he showed how you can create a clock using a quantum mechanical Hamiltonian, and then how you can use that clock to do controlled simulation or controlled processing of information. So the mathematical model is based on the principles of quantum mechanics. So you could actually, if you pick up a quantum mechanics textbook, you could actually go through all those principles. There are 6 or 7, depending on what book you are using. And for each postulate of quantum mechanics, you can actually infer something about the architecture of the computer. So since this is more physicsy, I will not go into that. But the postulates of quantum mechanics argues that there are some unique phenomena you will see in quantum world which do not have any classical counterpart. For example, quantum superposition, quantum entanglement, quantum measurement, and these phenomena actually enriches the model of computation and gives you some potential advantage when you calculate. So I'll also make a few more points about quantum computing. First of all, contrary to what typically you will see in the press, it is not a silver bullet for all computational hard problem. The computer itself is kind of a non-von Neumann architecture. So obviously, it is going to impact the way you are programming those machines. The data you store in the computer are stored in qubits, which are basically a special type of vector space known as Hilbert space. If you look up like in Wikipedia or in a textbook, it is a vector space with certain condition on the inner product. of the points in that space. Um, so so that's different from traditional quantum computing, where we solve problems in real space, which are encoded in a binary computing model. So the logical operations in a quantum computer are complex unitary processes. So that's different from classical computation, where you could write any classical algorithm as a sequence of unitary matrices, but those are not complex matrices. Those are basically permutation matrices. So that's little different. The readout is probabilistic. So it is similar to machine learning, where you typically run an algorithm multiple times and you kind of take a probabilistic measure of the result. So that's similar to in quantum computing. However, the reason it is probabilistic comes from the postulates of quantum mechanics, which says that if you want to extract information from Schrodinger's equation, you have to run the experiment again and again. So the last point is more like a cultural thing. Since the field is still very primitive, the problems we are trying to solve these days are still toy problems. So it is easier to communicate those processes as graphical models instead of pseudocodes. So that's what I meant in the last bullet point. So now that we have some basic idea, which is hopefully the brush up of what you already know, let's before going into all the details, let's take a quick look at how these machines actually look like. So there are multiple, since it is a primitive technology, we still do not know which architecture will actually work out. So people are trying different ideas, including researchers at UMBC. So there are 5 mainstream ideas: superconducting loops, trap-down architecture, silicon-based qubits, topological qubits, and diamond vacancies, or NV vacancies. So I'm not going all into details, but I thought you should at least know these names and you can look them up. So I'm going to talk about the first 2. UMBC actually has active research group, at least in superconducting loops. We also have active research going on related to photonic quantum computing, but I'm not sure whether we have actual trap-down groups yet. But there are groups at University of Maryland, College Park. So I'm going to cover the first 2. I also have experience with the first 2 at architecture. So let's talk about superconducting qubit quantum computer. So my focus will not be on teaching the physics of it. It's more like show you the scale of the system, different components at a relatively high level. But you can, for every slide, I have the sources. You can always go to that link and learn more. So superconducting qubit quantum computing is what I'm doing right now at IBM Quantum Computing. So I wanted to give you some idea about the scale. So this is the chip IBM used, designed in 2015. This was the first publicly available IBM chip. And this is the chip from this year. So from 2015 to 2021, so you could see the progress. There are lots of work by hand on the left panel, but this is totally fabricated chip, just like a commercial chip. So hopefully that will give you some idea how much work has been put in that technology in the last 5 years. It's a rapidly growing field. So what do we do with this chip? So let's take a closer look. So this is an electron micrograph. I'm going to talk a little bit about different components, but this is an electron micrograph, and these are not as small as traditional Intel chip. So you could actually identify these features if you look with plain eyes. You don't need any microscope or anything. So I have the color-coded version. So you can see the red rectangles; those are qubits. So what are the metals? So since this year we don't disclose the exact metals we are using, or exact combination of metals we are using in the chip, but this is from 2015. Back then, we used niobium loops with it's not a perfect loop, but there is some junction which creates some capacitance and other components to create capacitance and inductance. So, and when you cool it down into millikelvin temperature, it acts as a superconductor. So current flows either in the clockwise or anti-clockwise direction. And that's what you use to encode information. So let's say 0 is clockwise flow of current and 1 will be anti-clockwise flow of current. And when we say quantum superposition, we are basically creating a superposition of these two directions, which is not possible in a classical computer. So you know that the red rectangles are qubits. You need to read the qubits to extract the result, and you need to be able to write on the qubit so that you can program them. So we do that with these blue curvy lines. These are basically resonators. So you create electromagnetic induction there. And so when you are running a quantum program, you basically write your Python code, and that code is compiled into lower level representation, which goes into an FPGA-based electronics that creates microwave signal. That microwave signal comes to this inductor, and then it changes the flow of the current. So you also see these greenish curvy features. So those are basically used to couple multiple qubits. So when you want to do programming, you have to let these qubits interact with each other. And those inductors are used to create that effect. And you also have some buzz because you have to, you want to read out and program those qubits as efficiently as possible. So you don't want to have like individual channel for each qubit. In that case, you need a really complex 3D structure. So people do multiplexing. That's why you need a special bus to read out and control the read out from and control the qubit. So we have 5 qubits here, and the first public IBM quantum computer had 5 qubits. All right. So where does that chip go? Here in this hole. So I will explain that structures, but just to give you the idea. So you're looking at a fridge. It is called a dilution refrigerator. And you are seeing all these gold discs. At each level, the temperature goes down to a different value. And all the way down, now you are having millikelvin temperature. And onto that hole, you basically screw down that chip. So here's the schematic version of that fridge. Again, these white horizontal lines are those gold discs. And you can see that here you have 4 Kelvin. Now you're already millikelvin level all the way there. I think you have 15 millikelvin, and that's where the chip is. That's actually cooler than intergalactic space. All right, so to give an idea, now you can see how big the fridge is. And so my colleague Han-Hee and Sarah are actually working with the hardware itself. So we could see that actually a couple of people can fit within that refrigerator. And finally, we basically wrap it up with metal sheet when it is in production. So it's a typical data center. These are also publicly available pictures. So you can see there are 2 fridges in a quantum data center. There is one on the foreground and another one in the background. All right, and the total architecture of a quantum computing environment looks like this. So this table is basically your workstation. You're writing programs on this laptop. This goes down into a server, which compiles it into lower level representation, goes to the FPGA-based electronics, which creates microwave signal, which is sent to the refrigerator, which is at a different temperature. And that's where your program is being executed. Cool. So by the way, from this picture, it is kind of obvious that if someone is trying to have a career in quantum computing, you can come from lots of different backgrounds. You could be a traditional computer scientist who will be working at the algorithm and application level. You could be an electrical engineer, or you could be a mechanical engineer who will be building the fridge, and everything in between. Cool. Now I will switch to a different technology, which I had experience with in my previous work at IonQ, which is a quantum computing startup at University of Maryland, College Park. They recently went public. So that's a totally different technology from what IBM is doing. So what do they do? You saw that at IBM we are not working with individual quantum particle. We have a macro object. When we cool it down, it shows quantum behavior, and that's what we exploit. In trap-down technology, that's a little different. They work with natural quantum objects, which are basically ions. So, for example, I'm going to explain this picture, but just to give you an idea. So, at IBM, we encode the information in the direction of the current in a superconducting loop. At IonQ, they encode the information on the spin of individual atoms, individual charged atoms. So if you have spin half, plus half, maybe you have logic 0. If you have spin negative half, you have logic 1, and so on. So again, these are the two different chips, from one from 2015 and the one from 2021. You see lots of handwork went in there, but this is totally industrially fabricated. So that might give you some idea of how rapidly the field is progressing. So this is an ion trap. There is an opening here. Also there is an opening, and you can actually see these features in plain eyes. You don't need a microscope. Probably the length of this whole chip will be 10 millimeters. So in that opening, you apply rotating electric field to create a potential which is shaped like a ball, and at the bottom of the ball, the ions are stable, and they're just suspended there. Because of that rotating electric field, and then you shine lasers to change their spins, to basically change the energy levels, and that's how you program them or control them. So where does this trap go? It goes into a vacuum chamber. It could be about more than 100 pounds. You need actually like a small crane to pick it up. So you put the trap inside the vacuum chamber. It has a bunch of windows around it so that you can shine lasers, and you take the air out. Why do you need that? Because the ions are suspended in an electrical field, and if there are air molecules, they will be colliding with the ions, and it will corrupt your result. So you want to take the air out. You still need to have precaution, because when you create vacuum, the atoms from the inner surface of that chamber, the metal, those atoms will be vaporizing and will try to collide with the suspended ions where you are encoding information. So you need to be very careful how you are designing and creating this chamber and everything. Typically, people put this chamber into an oven for probably 2 weeks to get the vapor out, water vapor out. All right. So that vacuum chamber is put in an optical table with lots of optics and electronics. For example, those colorful cables are fiber optics. And this whole setup is part of a bigger optical lab. So this is probably pictures. This is actually a picture from an academic lab, run by Chris Monroe. Professor Chris Monroe is a professor at Duke. He used to be at College Park. But they're trying to make everything streamlined and compact. And for example, this is proposed by a different trap-down quantum computer company to create telecommunication, use telecommunication rack form factor to build commercial trap-down quantum computer. All right. So I know it was a little high level, but I wanted to give you some idea about the scale of those devices. Now let's talk about the problems we want to deal with quantum computers. Before going to those problems, I would like to make a few comments about the complexity aspect of that discussion. So I have a bunch of I have a Venn diagram, And in computer science, we typically divide problems into different classes, complexity classes, so that we can make general comment about those classes. So in this picture, uh, the the gray shapes are traditional complexity classes we see in theoretical computer science. The red and green are contribution from quantum computing. So you might be familiar with NP, non-deterministic polynomial time problems. So BQP is bounded quantum polynomial time problems. So, and QMA is basically the NP analog of quantum computing, quantum Marlin Arthur, the complexity class. So I kept some example from each one example from each class so that you can correlate what level of hardness we are talking about. So you already know Shor's algorithm. There is no polynomial time classical algorithm for integer factoring. So that problem is outside P. But since there is Shor's algorithm, it is going to be in BQP, which is the problems which we can efficiently solve using a quantum computers, right? So for example, traveling salesperson is NP complete, right? Finding the ground state of K local Hamiltonian, it is a problem defined in quantum complexity theory. So when people first discovered the complexity class NP, in that paper, the problem which was used as an example was satisfiability problem, 3 set. So when people define quantum complexity classes, they use the ground state problem. So we call it K-local Hamiltonian ground state problem. That's basically the equivalent of 3 set in terms of the hardness, not exact same hardness, but these are the hard quantum problems. BQP is the easy quantum problems. So what type of problem we want to solve using quantum computer? Definitely not QMA problems, because we will not be able to solve them using efficient quantum resources. So my understanding is that we are looking into this red, this area outlined by this red color. So we want to solve problems which are hard for classical computers, but easy for quantum computers. So example, integer factoring. By the way, within this region, there are actually lots of structure. So these classes are for exact algorithms. There is also a hierarchy of complexity classes for approximate algorithms. And so if you consider approximate algorithm, you can actually break down that region into this hierarchy. And so of course, as you increase the hardness of the problem, the cost of the algorithm goes up. And if you can solve that problem using a quantum computer, you're actually adding more value to the field. All right. So now I'm going to give you some perception about how the field actually evolved over time. I have picked some results. These are not like how hard the problem was. It's more about how different results impacted the field from a funding point of view or investment point of view. So the first 3 work, Feynman's paper, Shor's algorithm, and Grover's algorithm, they basically first created the first wave of attention to the field. So so this result basically created curiosity among the academics. So then, in 2005, there was a paper by Seth Lloyd and other co-authors who showed that you could actually do chemistry and physics simulation using a quantum computer. That was the initial intuition of Feynman, but the concrete algorithm was and the complexity study was first done with this paper, in this paper. And then in 2015, there was another paper which shows how you can use the near-term quantum computers to solve the physics and chemistry simulation problem. Again, the original problem which Feynman proposed. So, so with Seth Lloyd's paper, people knew how to use a fault-tolerant quantum computer, which is still probably at least a decade away, um, uh, to solve the problem. But then in 2015, that paper showed how you can use today's quantum computer um, to approach the problem. I can give you some concrete numbers so that you can have some understanding of the scale. So typically, if you're solving a chemistry or physics problem, you're basically simulating either the ground state or some dynamics of that molecule or that nucleus. So you have to map those orbitals to a quantum system, right? There are lots of different mapping, and it's a separate field within quantum computing. So typically, a naive way to map is you are mapping one orbital to one qubit. Even if you take the fastest supercomputer, probably IBM Summit at Oak Ridge National Lab, you will not be able to simulate a system with probably more than 50 or 60 orbitals, a general system. So if you have a 100 qubit quantum computer, you're already beyond the reach of the best supercomputer we have today. So at that scale, right now we don't have anything to do. I mean, we have lots of classical algorithm, but with very low accuracy. So that's what actually we are aiming for, right? So which means that right now we have 50 plus qubit computers at Google and IBM. Probably next year we'll have probably about 100. So we are already, by next year, we are already at the range which no classical computer can simulate if the molecules are complex enough. So these papers basically attract the attention of national labs, pharma industry, material science industry, and all these. Then I would also like to mention this tree paper, Grover's algorithm. Then in 2008, the HHL algorithm, which is basically showed how to solve a certain type of systems of linear equations with exponential speed up. And then in 2014, which I will cover briefly today, there was a paper from Google which talked about solving non-convex optimization problem with reasonable approximation ratio with near-term quantum computer. So these three results basically attracted the attention of the computer science industry, like data science, and basically attracted the attention of Silicon Valley. So they started putting money into this field. So to wrap up, basically whoever is building quantum computer are trying to focus on pharma, energy, transportation, finance, basically the hard problems computer scientists typically try to solve. All right, so what is the promise here? So this is not an exact scientific law, it's more like a cartoon. The x-axis is the size of the problem, y-axis is the time to solution. So this orange plot is basically the classical scaling of classical solutions, and the green plot is the scaling of quantum computer. So the solid orange line is what we have today. The point here is that even if we keep increasing the computing power, the slope will still be exponential. That's the dotted one. But our hope is that quantum computing will give us a different slope in the scaling, and that's where we'll have that advantage. This crossover point sometimes is known as quantum supremacy, although the usage of word supremacy is actually disputed. All right, cool. So let's go to the practical challenges of building a quantum computer, which will be a segue to the discussion of near-term quantum computers. Cool. So why building quantum computer is hard? So to do compute, we have to interact with the qubits. We have to control, first we have to control individual qubits, and we have to let them interact with each other. However, we will also try to shield them away from the environment so that they don't get corrupted. So these are two conflicting requirements, and that makes building a quantum computer really hard. Right? So just to give you an example about the noise level, the left plot is basically the fault statistics on a GPU, traditional GPU. So you see that every 50 hours you will see one fault, typically due to the cosmic ray. So if you are playing games, it may not be relevant, but if you are running a lattice quantum chromodynamic simulation, which will take 5 years on this GPU, you have to factor in those faults and write error correcting codes for them. On a quantum computer, every operation comes with some natural noise. There are multiple reasons why you are going to have noise. First of all, quantum computing itself is probabilistic, so there is this fundamental uncertainty coming from the postulates of quantum computing. On top of that, these are human-made machines, so there will be some other sources of noise. So every operation will come with some uncertainty, and you have to deal with it. Typically, the traditional way to do it is using fault-tolerant quantum algorithms, which takes lots of resources. That's why they're different from near-term quantum algorithm, where we do not use error correcting codes. We try something else. All right. So what is the NISQ quantum computing? I wanted to cover this topic because if you are interviewing at a quantum computing job interview today in the industry, most of them are doing near-term quantum computing. So that's something you will be asked about. So the term was coined by John Preskill at Caltech, and these are basically first generation quantum computers. The amount of computation is very limited. So if you recall Shor's algorithm, there is a subroutine called phase estimation, and phase estimation is basically computing the eigenvalues, and the precision of that computation is dependent on the additional auxiliary register you're using, if you recall it. And if you're reading out floating point values from a computation, and you're complying by IEEE floating point standard, you have about 20 qubits to store that result, and the number of gates for that algorithm will scale at the order of 2 to the power 20, right? So that's why it's a huge number of gates, and we cannot run that many gates. We probably can run only thousands of gates in today's quantum computers, which is way less than what you need in Shor's algorithm. That's why you cannot break encryption with today's quantum computers. But we still can do interesting stuff with near-term quantum computers. So that's it. It is all about. So that was the third bullet point. You can do only very limited quantum computing, the basically short algorithm or shallow circuit. The upper bound of quantum advantage is quadratic. So that's applicable for computer science problems. Typically, the optimization problems we solve in computer science, they can be framed as search problems. You are searching the result in an energy landscape or solution space. So for search problems, if you recall from the Grover's algorithm, for unstructured problems, the speed up is quadratic. So which means that it will not always be exponential speed up. So it will not always be like Shor's algorithm. Now it could still be attractive if you are adding value to an industrial problem. If you have some knowledge about the structure of the problem, you might have better speed up. But that exploitation of structure will probably happen at the classical pre-processing. All right. So how do we implement the algorithm? So typically, we translate a problem into the quantum native format. Probably you will translate that problem into abstract problem into some spin model or some other physical model, and you translate it in a way that a certain state of that physical model will give you the solution. Typically, the ground state or the most stable state will encode the solution. So if you're reading out from the quantum system, you will get a bit string, which is the configuration of the ground state, but will also be the solution to a computational problem. You typically create data state using a variational algorithm, so which means that it is going to be a parameterized algorithm, and you optimize those parameters using a classical stochastic optimization routine, which wraps that quantum algorithm. So using that framework, we can typically solve these two types of problems: simulation of physics and chemistry, hard optimization problem, which actually are very broad. If you combine those two, these are basically a billion-dollar industry if you can solve those problems. So for chemistry and physics, the advantage is well understood. We already know that it is very costly to simulate quantum systems. For hard optimization problem, advantage is still under investigation. Yes, for general search problems, we know it is quadratic, but what we don't know enough about individual industry-specific problems. So this is actually a big part of my role at IBM, or my team's role at IBM. Cool. So this is, I'm not going to focus a lot on this slide, but I always try to put some keyword down so that the audience can take this keyword and look them up. So for the first type of problem, the standard go-to paper is the McLean et al. The second type, which I will cover briefly today, is Farhi et al. 2040. All right. So you could see that for near-term quantum computers, the flagship algorithms are relatively recent. So these days, when we invent or try to optimize a near-term algorithm, it is typically a co-design process. So we work on a problem, we come up with an algorithm, then we understand that maybe if you design the chip in a different way, you can do more with that algorithm. So we give that feedback to the hardware people. They change their design, and then we try the algorithm or try a new algorithm. So these days, the NISQ algorithms are basically co-design process. We try to optimize an algorithm which helps us to make a better chip. When we make a better chip, it allows us to run a more powerful algorithm. All right. So let's take a closer look at how we can solve a particular problem using a near-term quantum computer. So I will be using, you're already familiar with the graphical representation of quantum algorithm. We call them quantum circuits, but still I wanted to brush up. So traditionally in computer science, we use pseudocodes, but I will be using quantum circuits. So this is the pseudocode for Grover's algorithm. It's a search problem. And I have used color-coded shapes to so that you can understand which part in the pseudocode corresponds to which part in the graphical version. All right. So what is our today's problem? So we are going to compute max cut of a graph. So typically, when I'm addressing a more physics or chemistry based audience, I change this example to a more natural science problem, like finding the ground state of a deuteron or something like that. But since my current audience is the students, graduate students of computer science, I'm using a problem we are familiar with in computer science. So the general max cut problem is NP complete, right? It has lots of practical application, and the best known exact algorithm, Gorman-Williamson algorithm, it runs in exponential time. There are approximate algorithms which are used in practice. So in that problem, you are asked to partition the nodes. It's a graph. You have nodes and edges. You have to partition the nodes so that you can maximize the number of edges which are cut. So for example, in this problem, the solution is 4, and there are 2 possible solutions, right? So you basically have those nodes into alternative partitions, right? So the first thing we want to do is we convert that, we take a binary representation of the problem. So let's say the partitions are 0 and 1, so different bit string will give you a different solution, right? So if the solution is all 0, which means all nodes or vertices belong to partition 0. If it is 1 0 1 0, it means the first and third nodes belong to partition 1, and so on. Oh, actually, it is 2 to the 4 equals to 16. So there are 16 possible solutions. So in a sense, it's a search problem, right? It's a search problem where the size of the solution space is 16, and there are 2 which are global minima or global maxima. Okay, so you might recall that whenever we have a search problem, there is a quantum algorithm, Grover's algorithm, which is probably faster than the fastest possible classical search algorithm. But Grover's algorithm is not a near-term quantum algorithm. You need a fault-tolerant quantum computing machine which can run arbitrarily long computers. So we have to do it with a near-term quantum computer. Because of the noise level, we can only run so many gates. All right. So we translated that problem into a binary space, and or integer space. If you had weights associated with each edges, that's the problem defined in the real space. So when we map it to a quantum map it to quantum mechanics, remember our step. First, we have to map it to a physical model so that we can program that on a quantum computer. So when we map it to into quantum mechanics, we are mapping it to complex vector space, which is exponentially larger than real space. So it is counterintuitive because we are supposed to find a needle in a haystack, and we are mapping the haystack to a bigger haystack. So how are we going to find that needle, right? Well, that's where quantum mechanics helps you. You might remember, if you recall Young's double slit experiment, which typically people study in high school or early college courses, there is a quantum mechanical version of that experiment. So basically where the light source is a single photon, and you can still see those destructive patterns which because of the destructive interference. So if you're when you are searching in a quantum in a Hilbert space, you could imagine those different search paths as a tree, right? Search tree, and different search paths are basically different quantum processes, probabilities, and they could have destructive interference. There is no analog for this in classical computing, and you could actually have destructive interference in among those search paths, and that actually reduces the total possible points you need to search, and for general search problems that gives you the quadratic speed up. So in practice you might be looking for speed up but fractional, but still at some value. So again, that's why that's what we are actually trying to hope for, how we can take advantage of quantum destructive interference in quantum space, and that prunes the search tree and makes the problem easier. So now let's map that problem into a quantum friendly language, which is basically a physical model. For each edge in that graph, we define this expression. I'm not going to go into the details, but if you want to look up, the sigma z matrix is basically one of the 3 polymatrices, sigma x, y, and z, and this comes from quantum mechanics. So this is defined in a way that so this is going to give you a 4 by 4 matrix, and the lowest eigenvalue occurs when the nodes are in the same partition. You get the highest eigenvalue for a pattern, binary pattern, when the nodes are in separate partition. So you define this for all the edges, and then when you take the sum, it gives you a cut. So different bit string will give you different, or bit string here eigenvector will give you different eigenvalue. Your goal is to find the largest eigenvalue. That will give you the max cut, because the largest eigenvalue will put most amount of edges incidenting on different partitions. And since we have defined it using a spin model, you can actually run this experiment on a quantum computer and measure the result. You're for this representation, you're maximizing it. If you want to deal it as a minimization problem, put a negative sign, you now have a minimization problem. So how do you find it? Sorry, I will take one step back. So we define it as an energy minimization problem, which is NP hard in classical physics. We know it since 1982 that finding the lowest energy state in a transverse spin Ising model is NP hard. When you map it to quantum mechanics, it is also QM hard for general problems, for general spin models. So it's a hard problem. All right. So now we map the problem into a quantum space, and we know that the solution is the ground state of the quantum system. So how do we find that ground state? We have to look for it in that Hilbert space, right? In that vector space. How do we look for it? We basically, for each edge, we vary the probability of the connected nodes being in the different partition or same partition. And we try to find a combination of these probabilities which gives us the lowest value of that C. So how do we vary the probability? So for each edge, we create a quantum circuit. It is parametrized. You see this gamma 1 over 2. So we don't have to focus on 1 for the subscript. So this is an angle you provide in this RZ gate. Hopefully you are familiar with the RZ gate. It's a standard quantum gate. So these are C0, C0, and in the middle this RZ gate. So this gives you the ZZ interaction. So if you change the parameter, it's basically an angle. So it's, if you're using a trap-down quantum computer, it is the phase in the laser signal. If you're changing the using a superconducting quantum computer, is a parameter in the microwave signal. And you basically, on your computer, you're basically writing in an angle between 0 to 2 pi. When you tune that angle, you are basically playing with the probability of these two qubits being in 0, 0, 0, 1, 1, 0, or 1, 1, which corresponds to playing with the probability of these two nodes being in the same partition or separate partition. And you do it for all the edges. So the quantum circuit will look like this. The edge between 1 to 2, edge between 1 to 4, edge between 2 to 3, edge between 3 to 4. All right. So which means that the structure of the graph is encoded in this this part, the middle part of the quantum circuit. What are these Hadamard gates doing? You initially create an equal superposition of all possible solutions. That's the exact thing you do in, let's say, Shor's algorithm, right? And what is the last layer doing? Those are our X gate, which is basically a bit flip, right? 0 or 1. So which means that you are not only looking at considering a particular solution, you're also looking into the other symmetry, the bit flip symmetry, and see if that is a potential solution, right? And that also has a parameter attached to it. So NearTerm algorithms have lots of parameters, and you basically play with these parameters. How? There is a wrapper algorithm which is classical. It's a stochastic optimization algorithm. So for each term C, you measure the qubit, you get the bit string, and each time you try to converge to a lower energy by updating those parameters. And at some point you stop, just like a classical approximation algorithm. So how do you prove the correctness of this algorithm? So based on the variational theorem, you could show that you might get different values, but you will not go beyond the true value, which is -4. So you can actually prove them, and that's the correctness of the algorithm. Okay. So that was kind of the overview of how a typical quantum algorithm, near-term quantum algorithm works. I will show the code briefly after this talk. So do we expect quantum computers to replace classical computers? Probably not. It is probably going to be like more like a co-processor based architecture where you will be mostly using an HPC facility to do most of the work, and sometimes you when you see a hard problem, you send it to a quantum oracle. It will give you the value, just like you use GPU today. Which brings us to this question: when you are going to send a problem to a quantum computer, and this is actually a rich field in computer science. I think back in 90s and early 2000, people spent lots of time to understand how to tell when an instance of an NP-complete or NP-hard problem is actually hard. So this is a plot from Zhu et al. Where they basically this plot is from a numerical simulation. This is for 3-set problems. The best exact algorithm for 3-set problem is DPLL, and DPLL is has a backtracking call in that algorithm, and the number of that call is basically decide the cost of the solution. So if you have a hard instance, you'll have lots of calls. If you have an easier instance, you have less call. So if you randomly generate these 3-set problems, and if you plot the ratio between number of clauses and number of variables against the number of calls you're having, you will see a phase transition at some point of the ratio. So that's how people typically understand the hardness, empirical hardness of NP-complete problems. So this is known as phase transition. So there are also, so these are for random problems. There are also similar approach for practical instances of NP-complete problems. So this is kind of state of the art, but this is also the starting point of understanding when to send a problem to a quantum computer. And this is a natural field for computer scientists to think about if they are trying to add value to this field. Physics typically will not think about this aspect. Okay. So one other thing, I recently basically took a look at 2 conferences. One is purely theoretical deep learning. One was a conference on pure theoretical deep learning. Another one is quantum machine learning. And I removed the term quantum from all the talks submitted to the quantum conference, and then I created a word cloud. So you could see that the typical quantum machine learning algorithms deals with subroutines which lies at the lower level of the stack in a machine learning ecosystem. So I wanted to make a point that we are not thinking about replacing classical computing. It's more like it will be an added option for solving the problem a traditional computer scientists solve. All right, so at this stage, I will switch to a different screen, and I will use Quizkit textbook. It's an open source textbook from IBM Quantum to show how you can solve a max cut problem on a near-term quantum computer. So if you are not familiar with Quizkit, this is a Python tool for quantum computing, and you can get free access to up to 16-qubit quantum computers using Quizkit. You have to create an account at IBM Quantum, then the computers will show up. You can submit jobs, and after some time you will get the value, get the result. So it's a Python library. So you could say, maybe I should increase the font a little bit. Okay, so here we are going to we'll walk through a code to solve the max cut problem. At first, it will show you how to map it to a spin system. Then it will help you to visualize the solution space. so that you can identify the global minima and the local minima, and then you will actually use the algorithm, QAOA algorithm, to solve it. So initially we are just using some standard Python scientific libraries. I will not go through the discussions, but I will cover the, I'm not sure, it seems like the edges are not visible because they are too bright. So basically here we have 4 graphs. So it is basically showing all the solutions of a 4-node ring graph. Right? So you have all the nodes in the red partition, you have 1 node in the red partition, and so on. Actually not all the solutions, because there are 16 possible solutions. They're showing 4 different solutions of the Max-Cut problem on a 4-node ring graph. That is the same graph I used in my example. So I will scroll down. So you might remember that QAOA is the flagship algorithm for solving optimization problem on a near-term quantum computer. It's known as Quantum Approximate Optimization Algorithm by Eddie Farhi et al. So this discussion is talking about how we defined the circuit. You might remember that we created a sub-circuit, C0 gate, RZ gate, and C0 gate for each edges, and it is basically defining the Hamiltonian for each of those quantum operation. And so if you take a look at the paper or at this tutorial, when you apply that circuit, it creates a quantum state, and this is the expression of that quantum state. You might remember that in my circuit I had 2 parameters, gamma and beta. It has beta and gamma, the 2 parameters. The psi naught is basically the initial state, which is the equal superposition of all possible binary basis states. You get that state after applying the Hadamard gate. Then you apply the sub-circuit which is parameterized by gamma. Then you apply the sub-circuit which is parameterized by beta, and you keep repeating them here up to p times. So in my example I used only 1 repetition, so that's why you had only 1 layer of gamma and 1 layer of beta, but you could repeat them again and again. But that means you are increasing the parameter space. So in the first chunk of code, you are basically defining the graph and plotting it. So you see that that's a 4-node ring graph, 0, 1, 2, 3. All right. So then you might remember we mapped the problem into a spin model. This is the Hamiltonian of the spin model. All right. And you can always plug in the values of these matrices and get an actual matrix. So these are polymatrices. For example, poly-Z matrix, identity matrix, and identity matrix. So this is probably for edge 0 between 0 and node 0 and node 1, and you are going to have 4 of them. And if you work it out, it will be a so 4 qubit, so a 16 by 16 matrix. So, and to apply a quantum gate or quantum operation, you have to convert the Hamiltonian into an unitary matrix, right? And how do you do that? You exponentiate the unitary matrix, Hamiltonian. That's how you apply a gate. All right. So this is the first Quizkit code you are looking at. These are IBM specific code, but you could also run Quizkit on other machines like trap-down systems. So the first few codes is basically allowing you to define the libraries for defining a quantum circuit, running it on a quantum computer or a simulator. So it takes the adjacency matrix of the graph and creates a 4-qubit circuit and visualize it. So now you see 4-qubit circuit and only 1 layer of gate, the NOT gates, right? Then you apply some more gates which actually encodes the structure of the graph. So now you're seeing all those sub-circuits I showed in the graph, and we had 4 edges, so 1, 2, 3, 4, 4 similar patterns. That's the structure of the graph. And you start with an equal superposition I already mentioned, and it is created by applying the Hadamard gate. The H function in Quizkit is the application of Hadamard gate. So you have the Hadamard gate. So when you combine these 3 parts, you have Hadamard gate, then the NOT gates, and the C NOT and the subcircuit which encodes the structure of the graph. And this expression is basically measuring the expectation value, which means that I'm reading out the result. And you might remember that NearTerm algorithms are hybrid algorithms. You have a quantum routine, and it is wrapped up by a classical optimization routine. The classical optimizer, quantum routine, and the result. So it's a loop going on. This is the pseudocode. You can always look it up. And basically, I will jump into. So these are basically post-processing code. So from a quantum computer, you will read a bit string. You have to convert it into the actual value of the cut. So this is where it happens. So these are post-processing, basic post-processing. So this is the function which generates the circuit. We already saw the code to create different components of the circuit. They basically package them into a function. All right. So you are using the encoding the. You're defining the beta and gamma, the parameters. You're defining the RZZ, which is basically C naught RZ C naught interaction. You're defining applying the NOT gate. Oh, also I missed the Hadamard gate. So these are all now inside the same function. Now this is where get expectation. This is a physics term, expectation value. You're basically measuring the bit strings and creating an expectation value, computing the expectation value. Here you're running the circuit on an actual background. So for example, this code says that run it on a simulator. Later on we also see how to run it on hardware. We are saying run it on a simulator, and we are defining the number of shots. You might remember quantum mechanics is probabilistic. So any experiments, we have to run it again and again. So we are defining how many times we are running. So here I'm running 512 times so that we can see the probabilistic distribution. In a typical chemistry and physics simulation, we sometimes run millions of times. I'm currently writing a paper which basically a variant of support vector machine. It's called quantum support vector machine. You might be familiar from your machine learning course. So we are basically running 1,000 shots. All right. On IBM quantum computer, we allow people to run up to 8,000 something. It is a limitation defined by the FPGA, electronics device control layer. So this is where we execute the circuit. We define the target machine or simulator. We define the number of the run of the experiment. So and you might remember the quantum routine is wrapped up by classical optimizer. So you can use any off-the-shelf optimizer. Here they're using Kobila. You might be familiar with this from machine learning. Typically on a simulator, we see Kobila performs better, but on an actual hardware, we see SPSA perform better because SPSA addresses noise and hardware is noisy. So you see that the result was negative 2.99. You might recall that basically 3. You might recall that the exact value is negative 4 from my slide deck. We found negative 2.99. We used p equals to 1, or first one iteration of the circuit. If you increase the iteration, you will see that the value is getting closer and closer to negative 4. But it will never go beyond negative 4, because that comes from variational theorem. So, and you could see that when you get the result, run it again and again, you will get a distribution because quantum mechanics is probabilistic, but the exact result is 0, 1, 1, 0, and its other symmetry 1, 0, 1, 0, they have the highest probability. on a software simulator, you will get them exactly equal, but on an actual hardware, you will see some variation. But these are going to be the highest probability, and those are the actual result. Oh, by the way, you might ask, this was a simulator, right? The chasm simulator, if you recall. Let me quickly go up. It was a simulator. So why we have difference? So IBM has more than one simulator. If you are using state vector simulator, which is basically which does exact matrix multiplication in Hilbert space, you will get exact same result. But the chasm simulator uses a Monte Carlo algorithm, which adds some noise. That's why you are seeing different levels of peak. So let's also so that's basically the framework of the algorithm. I will quickly go through the rest of the page now. For example, by the way, this is where you will see all the physics definition of this representation, and I will quickly jump through the physics hardware part of the algorithm. Okay, I'm sorry, it's really long. Oh, actually, interesting. So they removed the physics, the hardware part, but actually the only thing you need to do is so let's go back to the target where we define the target. So AR simulator. So instead of AR simulator, every quantum computer has a string associated to it. For example, the one I'm using right now is called IBM Dublin. It's named after Dublin. There are IBM Kolkata, there are IBM Montreal, and everything. So you will, when you log in, you will see the machines available to you. Probably the largest will be IBM Melbourne. You will write the exact same string, and then it will run on that hardware. Of course, you will have to skip this parameter SIT simulator because we are not using simulator anymore. And regarding the number of shots, the higher number means the algorithm will give you run slower because you are running a more run of the experiments. So of course, you will have a wider distribution in the sense that you actually, if not wider, flatter, because it's a noisy machine. So you will have a lower peak, and the other options will have some higher value. So the exact same code, you only need to switch the name. So this was today's lecture. Today we covered a bunch of items. So first we kind of defined the concept of near-term quantum computer and how that is different from traditional quantum computer. We discussed why building near-term quantum computer is hard. We had a visual tour of the two mainstream technologies for near-term quantum computers, superconducting qubits and trapped-band quantum computers. We also discussed what are the target problems for near-term quantum computing. Then we took a deep dive into the max cut problem and how we map that problem on a quantum computer, then use a near-term quantum algorithm to solve it. Then we spent a little bit of time on the future of the technology. And finally, we saw the code using the existing quantum computing software stack, how to solve the max cut problem on a near-term quantum computer and how to interpret the result. Thank you.